All right, welcome to section 2. Okay, so the big idea here is we defined essentially space and how we're going to build every figure in geometry, right? Points, lines, planes. Well, now lesson 1.2 is essentially saying let's attach some numbers to that, because with geometric objects we can't use algebra, and we spent a lot of time learning algebra to do all these cool tricks and solving, and let's attach some numbers to geometric space, and that's essentially what we're doing here. Okay, so big idea here is we can chop the infinite ends off of a line and just have a finite portion of it, right? That stops on one side and stops on the other. We could even measure the length of that. Units don't matter. I could measure it in terms of really small things like millimeters or really big things like miles. It doesn't matter, but I can quantify. I can give a numerical length to that using some ruler with some units, okay? And now that we have units, we can do algebra. We can add things, subtract, equal, solve for variables. That's the big idea of this section, okay? So let's first look at line segments, okay? So line segments can also just be referred to as segments. It's a finite portion of a line, so it's still defined by 2 points in space. The difference is now we have 2 endpoints. Instead of saying a line passes through these 2 points and goes on forever, right? In the last section it was and keeps going in both directions. Now the line segment stops at those 2 points. So it starts at point A, goes to point B, and there are no points outside. It's only the points between A and B. We'll even rigorously define what between means in a little bit, okay? So that's how we define a line segment, by the 2 endpoints in space. So in image form, it looks like this without those dashed arrowheads, okay? So we have 2 dots that are labeled with points, and then we have a line segment connecting those. Okay, in writing, we do the same thing that we did for a line, except we leave out the arrowhead. So we do a capital A, capital B, and we just, oh, I thought you guys could see that. So we just do a capital A, capital B, and then no arrowheads over it. Okay, couple notes, right? A line that's infinitely long, and a line segment is finite length, so it stops, right? Oh my gosh, and I did arrowheads on these. That's a crazy town. So this is line segment is finite length, okay? All right, now also as we start to do examples, we're allowed to make one assumption when we look at pictures, and too often people make many assumptions, and that's what leads to really failing in geometry as a whole, is because this is the study of logic, deductive reasoning. How can I get from A to B to B to C, from C to D, and chain together this logic without making logical like skips and leaps and bounds where I'm skipping over important steps that may or may not be valid, and then I end up at some invalid like nonsense, right? So the one assumption you can make when you look at a diagram is if a line looks straight, it is. We're not going to trick you with this being like 179 degrees, so it looks straight, but we're like, ah, gotcha, it wasn't. So if it looks straight, you can assume it's a line. So in this picture, you would say, oh yeah, A, B, and C are collinear. That angle in between is 180 degrees, so on and so forth. So you can assume that, and we're going to use that down below, okay? Now, we need to define the terminology around a length of a segment. So when we have the line over the AB, we're talking about the actual line segment, the geometric object, like a rock. We're picking the object up. We're saying, look at this object. It's so amazing. It's a geometry thing. We can't do algebra with that, okay? You can't say rock plus chair. Like, what does that mean? Are you gluing the rock to the chair? Or I don't even, that's a nonsense thing, right? You can't say rock equals chair. So all those things you learn in algebra, plus, minus, square root, those are for numbers, okay? You cannot do those with objects. So we need a new sort of terminology with how to deal with objects, and that's what we're going to develop, okay? A little bit down below, we'll make our own form of an equal sign called congruence, okay? But for now, just know you cannot do any algebra with geometric objects, and when the line segment right here is over the AB, we're talking about the object. Okay, when there is no line segment over it, and we just have the AB, now we're talking about the length from A to B. And we're defining this right now. This isn't something you should have already known. So when we don't have a symbol over the AB, we have 2 capital letters by themselves, that always means the distance from point A to point B in a straight line. Now this comes up a lot on like the first couple quizzes, and kids will walk up to me. I mean, this is virtual, but kids will walk up and the question will say like, oh, find AB. What is that? I don't understand. What's it asking me? And that's a terminology you need to adapt now, because that's going to come up all the time on quizzes and tests, okay? All right, so we've now got the length of a segment totally separate from the actual segment. We draw this as a numerical length, and this is the object. Since this one on the right is a number, we can now do algebra with it, right? So this absolutely makes sense. You're saying the distance from A to B, number, plus the distance from B to C, number. That's like 3 plus 5 equals 8. Like, that's totally okay. On the left, this is meaningless, right? Bird plus rock equals car. Like, that doesn't make sense, okay? So we want to be really clear on the difference between those two. All right. So now we could define what it means for a point to be between two other points. Like, could we say that point B is between A and C? Or what does it even mean to be a line segment? Like, to be all of the points between A and B. What does that mean? And so we define it. We can actually ask the question, is point C between points A and B? And it is, as long as portion of the journey plus the rest of the journey equals the entire length. So in this case, the distance from A to C, that's 3, plus the distance from C to B, 7, is equal to the distance from A to B, 10. So yes, 10 equals 10. Okay, C is between A and B. Now the reason this works is because, and over here, I wrote it, right? The shortest distance between 2 points is the straight line. And so if I were to have taken any other journey, if I were to go this way, then this way, I would have maybe gone like 4 and then 8. So I would have gone a journey of 12, even though if I would have gone straight from A to B, it was 10. And so what this question is really saying is, did you veer off the path? Did you go straight, the shortest path from A to B? Then yes, 3 plus 7 is exactly 10. All I did was stop on my way and then keep going, but I never veered off the path. I went the correct number of units to get from A to B. If I were to go off the path even by a little, I've now added extra journey into another dimension. So now I'm dealing with a triangle and not a straight line. So that's what betweenness is, okay? It's simply saying, is part of the journey plus the rest of the journey equal to the whole journey? Okay, we'll use that a little bit. It's not going to be something we use all the time, but it will come up on like quizzes and homework questions and stuff. Okay, so here we go. Let's do some examples, okay? Because that was really most of the lesson there. So example number 1, we've got this diagram. It says find A to B. Again, I know that without a bar over it, this is saying the distance from point A to point B. So this is 4. BC is the distance from point B to point C, or the length of the line segment, so that's 8. And then AC is the whole distance. And because I can assume this is a straight line, then I can just add those two distances. So that means this is a total of 12, so we get AC is 12. Okay, over in the other one, we've got the same thing, except now in reverse. Instead of adding 2 together, we're missing a length. But again, I can assume this is a straight line. So I know point Y is for sure between X and Z. So I know the short length plus the other length is going to add up to the total. So I simply go 12 minus part of the journey. That leaves us with 9 left over. So this is 9. Okay. But we could also introduce variables, right? Now that we've got numbers, we could do algebra. So in this case, we've got find QP, and we go, oh, shoot, you know, QP is this 2y. I don't know what to do with that. And you go, well, if I have a variable, is there an expression that I could set up that these two are equivalent? And if I can make an equation, I could solve that for that one variable, right? So here I go, oh yeah, look at this. I could say this total, 2y plus 21, is equal to this total, 3y plus 1, because they're talking about the same total segment, right? And so now we can do some algebra. We could take 2y from both sides, okay? And we could take 1 from both sides. And so we get y equals 20. Now, common mistake is just stopping there and going, woo, answer's 20, I'm done. Always, whenever you start kind of diving into a solution, take a step back at the end, take that deep breath. Deep breath is nice, you guys. Okay. and see what it's asking. It's asking for QP. So actually QP here was 2i. So that's equal to 2i, or 2 times that 20. And so QP is equal to 40. Okay. I'm going to make a couple more notes here before we stop, but that was the core of the lesson, right? Again, the lesson is just what is a line segment, okay? And then we can define the length of a line segment. Again, no symbol above here. That's the big thing. We're talking about that. It's a number. We can do algebra with it. And then just we start using it, okay? But as I mentioned, we want to be able to talk about like equivalence of objects, okay? And that's gonna help us do some more complex examples and really shorten the explanation we have to give in each problem, okay? So basically what congruent means is it means it's the same geometric object, but maybe it's with a different name. Maybe I took this triangle and I renamed the points from A, B, and C. I named it D, E, F. And I kind of spun it around and moved it in space. But I didn't change any numerical like length or distance or area or stretch it or tweak it. Nothing. I picked up a glass of like water or something and I just moved it to a different part in the table. Okay? And it's still the exact same. Every measurement you could possibly measure is exactly the same. That's what the idea of congruence is, okay? The reason I say I'm defining it loosely here is we're actually going to define it for each figure. So what does it mean for two triangles to be congruent? What does it mean for two angles to be congruent? And we're going to give a specific definition for each thing, and you'll start to see they make sense. The idea for line segments is they only have one thing. Right? There's only one quantifiable measurement, and that's the length. There's literally nothing else. It has no thickness. It has no like height, depth, anything, no width. It's just got a length. It's a one-dimensional thing. So if two line segments have the same lengths, that's it. That's their entire description. So then, yeah, they're the same. So that's the idea. We're going to define it for each shape, okay? We have symbols for it. So just like we have equals for numbers, we have this symbol for congruent. And so for congruent segments, we just say two line segments are congruent if and only if they have the same length, since that's their only measurement. Okay, so if I have a line segment of 5 and another line segment of 5, those two line segments are congruent, right? They might have different names and be in different places in space, but if you line them up, they're the exact same length. All we did was just move them to different places, okay? Again, the symbols here we could use in writing. We use this equals with a wavy sign over it. And even later in the year, it'll really make sense why there's a wavy line over it. Like, what does that mean? It'll click around chapter 7 or so. Okay. Here, though, in a picture, we signify it in a different way, okay? We use the same number of dashes on the segment. So I might have a more complex diagram. Whoops. Like, I don't know, like say it's a squarey, rectangle-y thing. I could put 1 dash here, 1 dash here to say those two sides are congruent. And I could put 2 dashes here and 2 dashes here. And that would mean something like this is 5, so that means this is of length 5. And if this was 8, this would be of length 8. So as long as you have the same number of dashes, that means they're congruent. And so that's how we use it in an image, which will be really common, just reading the textbook and noticing what they're giving you. Rather than writing out in sentences, they do it in the image, okay? And so here's another example. So it tells us that BQ is 6. Again, there's no bar over it, so it means the length of line segment BQ, or the distance, is 6. And then it says find BP. Well, what the heck am I going to do? Well, look at this. It says this line segment 1 dash is congruent to this line segment 1 dash. And this line segment 1 dash. So all three of those have a length 6. Again, we can assume this is a straight line. And so since these points are between, we can just add up those pieces of that straight line journey and say, well, 6 plus 6 plus 6, that's a total of a distance of 18 from point P to point B. All right. I hope you guys enjoyed that. Much shorter than the first one, way less to define there. All right. And then next section, we'll be looking at midpoints and distance formula. All right, guys, enjoy.